Hi everyone. The lesson today is about using the concept of contrapositive in order to prove different propositions. So first let's review. If we have proposition P implies Q, now P and Q could be any valid statements. So for instance, let's say that P is the statement, it is raining, and Q represents the statement, the road is wet. So remember, this symbol here is implies. So it translates to, if it is raining, there's an implied if. If it is raining, this implies the road is wet. I don't think anyone would disagree with that statement. Now, the contrapositive version of this statement, contra means reversed, and contrapositive. So we reverse the statement. Now we know that you cannot just reverse an implication. That wouldn't necessarily be true. If the road is wet implies it is raining. Well, no, that's not true. Sometimes it stops raining, but the road remains wet for some time. However, if we negate each of the statements, this fixes the problem, and that's what a contrapositive version of a statement is. So this reads, if the road is not wet, this implies it is not raining. Now that's fine. And so we use contrapositive sometimes in order to do proofs. Occasionally we'll be given a proof, we'll be asked to prove a proposition that looks like this form here, but it's difficult to do. So instead we write the contrapositive version of that statement, and these two things are equivalent. If one is true, the other must be true, and vice versa. We could say P implies Q, then the contrapositive, not P implies, not Q implies not P. So if I take that statement there, and I take its contrapositive version of that statement, then we can do one of these double-headed ones, which means that they are equivalent statements. Proving one is as good as proving the other. So sometimes we use a contrapositive version. Now let's take a quick example. And this is the one that we looked at in class the other day. So the statement was, we were required to prove for all numbers n which belong to the set of positive integers, if 3n plus 1 is even, then n is odd. That's the statement we have to prove. So let's take a look. This part, 3n plus 1 is even, that would be proposition P. So if this proposition is true, then that's the implication. Then n is odd, that would be statement Q. That's our version of the implication that we're looking at here. Now, I'm going to go straight to writing the contrapositive version of this statement. I'm going to write not Q implies not P. And this is just still a different version. Why did I put that? That should be a P for prove, required to prove. So this is just a different version of the statement. So I'm going to go, what is the opposite of n is odd? Well, that's n is even. Then I should have said if n is even, then what is the opposite of 3n plus 1 is even? Then 3n plus 1 is odd. So let's take a close look at that. N is even. That's the opposite. That's not Q, isn't it? implies 3n plus 1 is odd. That's the opposite, that is not p. Now I think we'll find it much easier to prove this. So we begin by saying let n, we start from the premise, let n equal, well, if it's an even number it must be a multiple of 2, so we'll go 2 times some other number p, and we will make a note that p shouldn't be fractions and things like that. P would have to belong to, now remember we had a restriction that n was a positive integer. Positive integers are 1, 2, 3, etc. Well, if it's an even positive integer, if it's even, it'd have to be 2, 4, 6. So p would have to be an element of the numbers 1, 2, 3, and so forth. In other words, the natural numbers. We could have said p is an element of the natural numbers, and that's just the two statements are just as good. So let's see, we've got n equals 2 times p, where p is one of these natural numbers. Now that's where we start from, but we want to get to this stage here of having 3n plus 1. So we build this up. Well, if it is true that n equals 2p, then logically enough, 3 times n would equal 6 times p. And the next bit, we want 3n plus 1. If I add 1 to both sides of this expression, 6p plus 1. Now here we go. We're almost there. I can tell we're supposed to prove that 3n plus 1 is odd. Well, any multiple of 6 must be an even number. In fact, I could probably make this even more obvious. It's obvious enough as it is. But I could write this as 2 times 3p plus 1. Now this bit is a multiple of 2. So this bit must be an even number. And any time I have an even number, add 1 to it, then the total thing must be an odd number. And therefore, I'm just going to ignore the phone while I finish this. Therefore, what can we say? We can say that 3n plus 1 is odd. Odd, and that means that our original statement is true by contrapositive. So by contrapositive, my original statement said if 3n plus 1 is even, if 3n plus 1 is even, then n is odd. That's the end, so that's where we put the QED. It takes a little while to get used to this, but keep at it, keep practicing, and it'll soon feel quite natural. Thanks for watching.